the universe continues to expand more and more. In 1929, scientists discovered that our bodies are composed of chemicals that originated in the cores of stars. By 1957, we realized that the sky is not only a beautiful thing to behold but also reflects the immense power of the universe. There is so much going on in the cosmos that, in most cases, we have no idea what is happening. We keep wondering why we exist, why there are planets and stars, and what other possible destinies might have been. Often, we don't pay attention to problems until they become critical, even if they will eventually affect us. Betelgeuse, one of the largest stars in the firmament, has begun to show signs of instability, trembling alarmingly, which could indicate that something frightening is happening. This star has been the subject of study because of its gigantic size. In fact, it is so huge that it makes our Sun seem tiny in comparison. It is not a star like other stars and never has been. Betelgeuse is a red supergiant, much more distant than it appears from Earth, more than 640 light-years away. Although this distance may not seem significant at first, in cosmic terms, it is immense. Even if we could travel at the speed of light, it would take more than 640 years to reach it, something impossible with current technology. Under normal conditions, it would take us more than 12 million years to complete such a long journey, which is much longer than the entire history of mankind. This gives us an idea of the magnitude and strength of the star, which has been shaking intensely for some time now. The stars, although they appear quiet from our perspective, are in fact not quiet, regardless of their size. Scientists do not yet fully understand the signals Betelgeuse emit. It has been labeled a pulsating red supergiant for a long time, and its brightness varies in cycles ranging from 10 to 100 days, depending on whether it is expanding or contracting. These gradual changes show us how dynamic the star is. Another interesting thing about Betelgeuse is that its brightness varies considerably, ranging from magnitude 5 to magnitude 0, which is a big difference between stars. These variations in brightness occur in cycles. The shortest cycle lasts approximately 185 days, while the longest cycle is 2,335 days. Occasionally, these changes occur more regularly and can be measured accurately. In February 2021, the V-band value of 1.1614 was one of the lowest recorded in recent years, deviating from Betelgeuse's usual brightness. Not only is its brightness remarkable, but also its intense red color, which is due to its surface temperature of about 3,500 Kelvin, much lower than the Sun's 5,500 Kelvin. Although the Sun is smaller than Betelgeuse, the latter emits less energy per unit area due to its lower temperature, which makes it appear less luminous. Despite being one of the largest known stars, Betelgeuse has been relatively stable despite being a pulsating giant. However, it has recently shifted from a calm state to a more unstable one, which is alarming. This is because Betelgeuse's gas shell is burning. It is gradually running out of hydrogen in its core, where the fusion process converts it to helium, which is expected in a red supergiant. As hydrogen fusion in the core slows down, the outer layers of the star expand, causing it to grow in size. In this phase, helium accumulates around the core, which is now mostly hydrogen, and the fusion process known as helium envelope burning begins. In this process, helium atoms fuse to form heavier elements such as oxygen and carbon, releasing energy that combats the gravity trying to compress the outer shells. However, the burning of helium is not as constant as the fusion of hydrogen in the nucleus, leading to accumulations of energy that are released irregularly. These energy releases can destabilize the star's structure, causing its outer layers to expand and contract, which manifests itself in pulsations that alter Betelgeuse's brightness over time. These pulsations release enormous amounts of energy, generating strong stellar winds that tear large amounts of mass from the outer layers of the star, a phenomenon characteristic of red supergiants like Betelgeuse. These stellar winds cause stars to lose mass, which alters the distribution of matter and energy within them and further affects their evolution. As the outer layers of the star expand and contract, a constant pulse is generated that we perceive as changes in its brightness, similar to the beating of a heart. To better understand these phenomena, astronomers employ a variety of methods. Among the most important are photometry and spectroscopy. Photometry measures the amount of light emitted by the star at different times, allowing us to observe changes in its brightness, as is the case with Betelgeuse, whose pulsations give us clues about what is happening inside it. This method provides a direct connection with the behavior of the star, facilitating the monitoring of its luminous variations. On the other hand, spectroscopy analyzes the star's light at different wavelengths, revealing key details about its temperature and motion. When Betelgeuse pulsates, its spectral lines change, allowing us to learn more about the processes behind these pulsations. Together, these methods allow scientists to build a complete picture of stellar behavior. By combining information from brightness analysis with that from internal structure, astrophysicists go further, using powerful computers to create models that simulate the inner workings of the star, from the equations that govern its structure to the nuclear and fluid dynamics at its core. These models make it possible to predict how the star's pulsations change as internal conditions vary, connecting theory with observed data. A fascinating process that occurs inside stars like Betelgeuse is stellar convection. Energy generated in the core moves toward the surface, helping to balance internal processes with the star's external brightness. As hot matter in the core rises and cooler matter descends, convection currents form that transport energy to the outer layers. This movement of matter alters the luminosity of the star, making it appear brighter when the energy reaches the surface. These changes in energy flow, caused by convection currents, are responsible for the variations in brightness that we observe as pulsations. The amount of energy moving within the star fluctuates, which explains the periodic alterations in its luminosity. Additionally, these pulsations are not just random fluctuations but can follow regular patterns, particularly in stars like Betelgeuse, which are classified as variable stars. The cycles of brightness are linked to the rhythmic expansion and contraction of the star's outer layers. As the star expands, the surface cools and dims, while during contraction, the surface heats up and brightens. The process is a result of complex interactions between gravity and radiation pressure. Gravity pulls the star's matter inward, while the pressure from radiation generated in the core pushes outward. These forces create a delicate balance, leading to the star's periodic expansion and contraction. Over time, this cycle can cause the star to become noticeably more or less bright when viewed from Earth. Betelgeuse, nearing the end of its life cycle as a red supergiant, exhibits these convective and pulsating behaviors more intensely. As the star depletes its nuclear fuel, it will eventually undergo a supernova explosion, marking the end of its life. Until then, the pulsations caused by stellar convection continue to influence its luminosity, offering astronomers valuable insights into the internal dynamics of massive stars.